All right. Why is that still there? Oh, I see you've decided to stop connecting. Okay, so we're going to kind of continue where we left off last time, however long ago that was. We were talking about interactions between molecules, and we had talked about dipole-dipole interactions, which were where polar things had, they had partial positives and partial negatives that could interact with each other. And we also talked about hydrogen bonds, which were a special case of dipole interactions, where hydrogen is bonded to nitrogen, oxygen, or fluorine, something very electronegative and small. And hydrogen also being small, we saw that those become stronger than plain regular old dipole-dipole interactions. So we're going to see a couple more types of interactions here today. And then we'll start talking about, the kind of the ramifications. What's the outcomes? What's the point of learning all this? How does this affect various properties? So the last one that we're going to talk about that's new for us is going to be what's called London dispersion. And so these will be a new one for us. This can be done. Let's just refresh our minds. So this is for polar things, right? Hydrogen bonds are polar with H bonded to F, O, or N. These ones are going to be anything with electrons, which is everything, right? So anything with electrons can undergo London dispersion forces. But it's easier to describe with kind of a just general blob. So this could be a molecule or an atom. And here's another one. We have two blobs. Okay, maybe these are hydrocarbons. Maybe these are xenon atoms. Maybe these are, water molecules. Whatever. Anything with electrons can do this. So general blob here. So general blob has electrons all over the place. Just zipping about. They're all in their orbitals doing their thing. But perhaps for a very, very short fraction of time, just as these are all zipping around all over the place, going very, very quickly, maybe at one point we end up with more electrons on one side of the molecule, just for an instant of time. That causes what's called an instantaneous dipole. So it's not a real dipole, it is a fake dipole. Dare I say. Instantaneous dipole would be a very, very small charge. It just happens that most of the electrons in this blob just happen to be on one side of the molecule at a given time. Just a snapshot, as it were. That makes the other side very, very slightly positive. What's interesting with this is that this can cause what is called an induced dipole. So maybe the other blob also, had a normal, electrons are all over the place zipping about, but those, maybe they see the other atom or other molecule, the other blob, and they're like, wait a second, what's going on over there? Let us all do the same thing. Let's go ahead and move, over to that side of the molecule. Because if the other side of the adjacent molecule is slightly positive, the electrons might be more attracted to it. Right? They're just more likely to say, hey, what's going on over there? I'm going to maybe just hang around this side of the molecule for a second. And that can cause a favorable interaction between these two. Generally, things tend to repel each other because they're all made of electrons. Electrons are negatively charged. They're going to be repelling each other. However, if all the electrons are on the other side of the molecule, just by happenstance, instantaneous, very short duration, that can attract another molecule to move its electrons a little bit towards that side of the molecule. And so this is what a London dispersion force is. It is very weak. Though it increases in strength with more electrons. So the more electrons you have, the stronger this force becomes. So you're going to see that this is what hydrocarbons mostly do. And you're going to see as hydrocarbons get very big, if you start having, 18, 20, 30 carbons, you have tons of electrons in there now. Those are going to actually eventually become pretty substantial. And so we're going to see that this force increases with the more electrons that you have. However, typically it is a weaker force than the other two that we've talked about. All right, so how it works, electrons zipping around happen to be on one side of the atom at one given time. That induces another molecule or atom to do the same thing, and those can have a favorable interaction for a short period of time before the electrons go ahead and disperse again. So this is very short-lived, fraction of a second, and it can induce another dipole in another molecule or atom. Cool. We have previously seen ion dipole, or have we in this class? I don't remember. Have we talked about ion dipole interactions? Like with water molecules? Something like this? Someone tell me, because that will determine if we need to spend some time on this. Doesn't ring a bell. Okay. So, in solutions, we know that soluble ionic compounds will dissolve in water, right? Okay, then I guess we'll talk about this one. So this is ions plus polar molecules. So we have seen previously that water has those positive hydrogens. Could be either one, Shane. The blobs could be anything. They are just generic blobs. Yeah, kind of. Yeah, it's exactly like that. So you can magnetize something. Though magnetizing iron can stick around for a long time, this thing just goes away pretty quickly. So, but yeah, it's kind of the same idea. Yeah. So Shane, these could be either molecules or atoms. Doesn't matter. I see. I think I misread your question. These would be one molecule or atom interacting with another molecule or atom. So whether those are, just an atom with all these different orbitals or a molecule with all those different orbitals, one of each. Cool. Alrighty. So, since water is positive, that's our typical solvent here. Water is positive on one side, negative on the other side. The positive side can interact with anions. And the negative side, the oxygen side, can interact with cations. So we can see here the sodium would be surrounded by these water molecules, and typically you're going to see that it's going to be the oxygen side that's nearby the sodium, because the oxygen side of those waters is what's attracting them. So because that's the negative side of the water, sodium is positive, so they're going to interact together. Just like before, we're going to see that this is going to be stronger than plain old hydrogen bonding. So compare that versus this. If we look at this, just make this a different color. There we go. The difference here, actually you guys can tell me, what's the difference between these two interactions here? So maybe we're just looking at I'll circle it. Let's see. Comparing this to that. What's different between these two interactions here? Water with another water or water with a sodium ion? What do we see as the difference? Yeah, Shane, that's absolutely right. Sodium is going to be more positive. And we saw that because the interactions depend on the magnitude of the charge, ion dipole is stronger. So, exactly. So, hydrogen has a partial positive charge. In your homework this week, you're going to learn how to calculate the partial charge. So, that's all going to be kind of self-contained within the worksheet. It's going to give you the formula and the constants you'll need. So, I'm just going to leave that to you. It's just using a formula to figure it out. So, you guys can deal with that. You'll be able to see what the charges are. So, we have a charge of +1 and a charge of less than +1. So, of course, +1 is a better option there. Okay, so ion dipole is going to be a stronger force. And then, of course, we have ion-ion interactions, which we just call ionic bonds. Those are going to be something like, something we've seen before, where we have full charges that are attracted to each other. And as you can imagine, this is even stronger than ion dipole because this is ion-ion. Both things are fully charged. So if we're to rank these, we're going to see that, the book actually has a pretty interesting chart. I'm going to try and replicate it here. Okay, these are going to be the weakest down here, and these are going to be the strongest. I'm going to write this a little bigger. Ion, ion. So we're going to kind of have a little handy-dandy chart here. We're going to see here that is this... first thing to look at is, do we have ions? In something. If you do not, you'll go to the left side. If you do have ions, you'll go to the right side. And so you kind of have, we're going to kind of make a little flow chart here. If you do have ions, you have to look at, do you have polar molecules also? If yes, then you're going to have ion dipole forces happening. If you do not have polar molecules around, you're going to have just ionic bonding happening. If you do not have ions, you want to ask yourself the same question rather. Do you have polar molecules? If you do not, then you have London dispersion forces happening. As you're like, if you're trying to find what your strongest force is. If you do have polar molecules, you have to see, do you have one of those three bonds? Oh no, and I'm out of space. Let's see if we can fix this. Oh my gosh, go away. Okay, we're going to just make this a little bit. Get out of here. Okay. If you do have a hydrogen bonded to one of those three elements, then you can have hydrogen bonding. If you do not, you will just have dipole-dipole interactions. So we have these kind of questions to ask ourselves. And we can kind of use this sort of like dichotomous key thing here to see what kind of forces we're going to have happening in our molecule. So this would be a chart to figure out what is the strongest force that you could possibly have. Let me, I guess I should have used various colors with this too, but oh well. Let's just make things a little bit more obvious to us. So just comparing our different types of interactions here that could happen in between molecules or atoms or ions. We have kind of 5 of them here. And we're going to see that the ones involving the most charged things are going to be the strongest, and the ones involving the least charged things are going to be the weakest. So London dispersion is barely charged at all, right? You have partial charges. So very, very small. And those are instantaneous. They go away very quickly, and things, go on with their lives. And we're going to see that kind of in the middle, we have the dipole interactions, and a stronger version of that is the hydrogen bond. And then in our strong kind of category, we're going to have ion dipole forces and ion-ion interactions. Again, those are full charges now. So we have permanent dipoles. Let's see. Here we have just induced dipoles. Here we have permanent dipoles. And here we have full charges. So remember, these are partial charge. And here we have partial charge. Partial. So, point is, the more charged your thing is, the stronger your forces are going to be. Hooray. If you have no charge, you're probably just going to go through London dispersion. So let's see. let's look at all the ways that water can interact with ammonia. Let me just give this chart a title also. Goodbye, sodium chloride. Okay. So Kevin is absolutely right that the strongest force there is going to be hydrogen bonds. So do we have ions in this mixture of water and ammonia? No, we do not. Do we have polar molecules? Yes, we do. Do we have hydrogen bonded to fluorine, nitrogen, and oxygen? Yes, we do. So Kevin has found that our strongest bond that we're going to have here is going to be hydrogen bonding. Or not bond, strongest interaction will be hydrogen bonding. So that's one thing it can do. What else could it do? Are there electrons in water? Yeah, we can also have dipole interactions, right? Because hydrogen bonds are just a special type of dipole interactions, for sure. And of course, yes, it has electrons, right? So it has to be able to go. It can do London dispersion also. So these are the three things that water can do with ammonia. So we're not limited to just hydrogen bonding. It could do these other things. However, these other things are going to be kind of pointless compared to the hydrogen bonding, but they could still happen. All right, so yeah, let's see. So yeah, essentially you just want to be able to kind of identify what things can undergo. So everything can undergo London dispersion. Chances are I'm probably just going to ask you what's the strongest force that's going to happen between a set of molecules or atoms, and you're going to probably be able to follow this chart to figure that out. So what the heck's the point? We're going to see that many physical properties are explained by these. By intermolecular forces. So a couple that we've already talked about is interesting here. Something we've already talked about. Yeah, boiling point is absolutely a big one as well. So something we've already discussed is when we talk about our solubility rules, we kind of, generally made the comment, if the substance prefers water than itself, it will dissolve, or if it prefers to stay as ions, it's going to be solid, right? We're going to see this as just a matter of which one of these will be better. So will all of the ion dipole forces that something undergoes be stronger than the regular ionic bond? That's what's going to determine if something will dissolve or not. So, we may be able to think, okay, well, hold on. We have sodium chloride, which has full charges. We're expecting that to be a stronger force, more attractive. But if we go back to that kind of thing, we're going to see that we can actually have many water molecules that can surround that sodium and interact with it. And we're going to see, so I've drawn 5. I don't quite remember exactly how many it's going to be in real life, but 5 of those ion dipole forces it tends, or is going to beat out the ionic interaction that sodium would have with chlorine. So this is more favorable for sodium to be surrounded by waters than it is to be next to a fully negative ion. So it just so happens that that's the reason that things with sodium are stable, is because the sodium can have so many waters around it that are going to help stabilize that ion, and that's going to be a favorable interaction for all these different things. So that's something we've already seen. As Kevin has said, a very big point is going to be the boiling point or the melting point. But let's focus on boiling point. Yeah, let's just do that. We're going to have others like viscosity. We're going to have surface tension. And we're going to have capillary action. We're also going to kind of have vapor pressure associated with the boiling point. So we're going to see that. So we're going to see that all of these are due to molecules wanting to maintain attractive interactions. So if a molecule has a lot of intermolecular forces, aha, but that's what I said, Shane. So compare one sodium versus one chloride versus one sodium with 5 or 6 waters. We're going to see that those 6 waters, that's 6 ion dipole interactions, and it just so happens that that's going to be enough. If you want, I do have, let's see, I think in your book there's also energies given for this. Let's go ahead and look, because I'll never remember these numbers, but I can prove this to you. Let's see, where would we be? What chapter are we even on? 11, yes, okay. So, no worries. Yeah, thank you, Kevin. We're on 11, yeah. Okay, so let's go ahead and I'll put some numbers for you guys with these. So for London dispersion, apparently that's between to 30 kilojoules per mole. Dipole interactions are between 2 and 15 kilojoules per mole. Hydrogen bonds 10 to 40. And these are just depending on you know, for London dispersion, it's depending on molar mass. For your dipole-dipole interaction, it's depending on how polar your thing is. So that's why these are as ranges. So I don't know that we can see any of these numbers that I've just thrown in there. But we can see ion-ion forces are about 150 kilojoules or more. And ion dipole are about 50 or so to break. So this is the energy it would take to break all of these interactions. So we can see that if we have multiple ion dipole interactions, say 5 or 6 of them, that would be 250 or 300 kilojoules per mole to break all of those. However, one ion-ion interaction is only 150, so we can see here that it's going to be more favorable to go with the more stable one, which is multiple ion dipole interactions. So what we need to remember here, it always takes energy to break bonds. Remember we talked about this when we were talking about bond enthalpy? We're going to see, yes, it always takes energy to break bonds. So we're going to see it's the same case for these intermolecular forces as well. Those are not full bonds, but they are kind of like fake bonds. and it's going to take energy to break them. And we are going to see IMFs will decrease as temperature increases. So, we kind of made the comment in the gas chapter that, gases tend to behave more ideally at high temperatures because we said gas molecules don't interact with each other. However, they would have London forces. If they were to get close enough and one of them happened to have those, electrons on one side, that could create a small, attractive force between two gas atoms. And we saw also that the molar mass was something that also kind of got away from ideal behavior. And we saw that heavier things with more electrons, tend to be less ideal. So the same idea is true here. So we're going to see that intermolecular forces will decrease with increasing temperature. So the more energy you give it, the more likely they are to break free of these bonds, and we're going to decrease the intermolecular forces, and therefore we're going to decrease all of these sorts of things. Okay, so let's talk about boiling point after. I'm going to talk about viscosity, surface tension, and capillary action first. So, viscosity. This part is just going to be a bunch of vocabulary. Viscosity is resistance to flow. And that means that it moves more slowly. So more viscous means it moves more slowly. So if we're comparing something like honey versus water, we know that honey is going to be more viscous. We know that if we try and pour honey, it's very slow. You hold the jar upside down, it's like dripping, pretty slowly, right? However, if you did that with water, if you took a water bottle and poured it upside down, the whole thing is just going to come out right away. And we're going to see that as temperature increases, these things get less viscous. So if you put your honey in the microwave or warm it up in like warm water or something, it's going to become less viscous because the interaction between the water and the sugar molecules is going to become less. So there is more hydrogen bonding in honey. That's why, because goodness gracious. So glucose or fructose have many OH bonds that will hydrogen bond with water. You don't need to know this. But that's the reason that honey is going to be more viscous, is because it's made of water and fructose usually, or glucose. And those both have a lot of hydrogen bonding areas that can interact with water very favorably. And so that's why it's going to be more viscous. Perhaps something a little bit more appropriate for us. Let's compare these ones. Which one do we think is going to be more viscous than the other one? What do we think? Yes. Yeah, you're both right. Except Tyler's spelling vicose. I like it. It's the French word for viscous, of course. So, yes, for sure. This one's going to be more viscous. And it turns out that this one is more like motor oil versus gasoline. If you wanted to kind of think of these, I know you're typing fast. Trust me, I do the typos all the time too. And so if you want to think about these motor oil, like if you've ever, changed your car's oil or something, it's pretty slow pouring, right? Versus gasoline moves pretty quickly. And also that's why, if you're going to get your oil changed in your car, you typically have to drive it around first to get the oil warmed up. The warmer, the hotter that oil is, the easier it is to drain out of your car because it'll move faster. Otherwise, it's a very slow process. So that's why you have to do that at an oil change. Cool. That's one that's down. Awesome. Surface tension. This is the, let's see, the, tendency of substances to maintain a low surface area. Typically this, no, we'll leave it as this. Okay. This is why if you take a penny, if you drop water on this penny, you're going to see that the water will form a kind of dome like this. Is because the water does not, or wants to have a low surface area. Yeah, exactly. Even in regular gravity, it will form a sphere. So raindrops are spheres as well. So spheres are going to be our kind of lowest surface area shape that we can make. But it's the reason that you can kind of keep putting drops of water on top of a penny before it spills out. So normally, you'd expect, gravity says the water should be at the lowest possible elevation, right? Because gravity wants everything to be close to it. However, the surface tension of this water will force it to kind of adopt this kind of dome shape on top of the penny instead of spilling out. So this is something you can try at home. Take a penny and take something that you can put little drops of water, maybe like a straw, or if you have pipettes for some reason, you can try doing that. Or you can just, just try and put drops of water. You're going to see that it's not going to spill all over the place until you get to a certain point. I'm dying. My goodness. This is also the reason that, here's our little water surface. You can have a little insect This is Shane the insect this time. Yeah, I probably have the Rona. I'm gonna die. Shane is a water bug. Can walk across the water. So, perhaps you've seen these if you've ever gone to a lake or a stream or something. You can see bugs that are walking on water. And the reason for this is the surface tension again. It would cause more surface area to for that insect's leg to break through the surface of the water. So the water, because it does not want to do that, is going to stay intact. No, Shane is not like Jesus. That's not what I'm trying to say. He's a ninja. Yeah, there you go. She's got the right idea. So I'll say Shane the water ninja. So that little bug there. Or how about this? We'll make Shane even more boring. Here's a thing of water. And Shane can be this paper clip that is floating on top of it. So, believe it or not, you can take a cup of water, and if you maybe have some tweezers or something, try and put a paper clip on there. You'll see that the paper clip will float. Even though the paper clip is denser than water is, you would expect it to sink. It's made of metal, right? It's because of this surface tension, exactly. So, because, yeah, right. Yeah, they tried to hype you up, and now you are downgraded to a paper clip. So now you're over here. Fun fact, if you put soap in this water, that will interrupt the intermolecular forces, which would cause the paperclip to sink. Black pepper will also float on water. Pretty cool thing to do there. And if you put soap into black pepper floating on water, it will push all the black pepper away because of this idea. So things with high intermolecular forces would have high surface tension. And so again, they want to, so surfactants would minimize that. So surfactants, notice it has the word surface in it. Aha! Surfactants are substances that interfere with intermolecular forces. And so if you add a surfactant to your water, like soap, for example, that will mess with your intermolecular forces, and that's going to ruin your surface tension. So soap typically is something that has a nonpolar bit, just like your lovely phospholipids. You're going to have a polar part and a nonpolar part. Typically, that polar part would be something like a sulfate group or something. Absolutely, yes. So every time you sigh or you have those big, big yawns, those are your lungs applying surfactant to your alveoli to help keep them open so that they don't collapse on themselves. Absolutely. Yep, for sure. So your body definitely does this all the time. So that's why, periodically every, 20 minutes or so, you let out a big sigh. And that's to help replenish the surfactant in your alveoli. So something like this would be a surfactant ravioli. For sure. So yes, these are important for biology. Me too. I'll just forget this. Let's go have lunch instead. So the point is here, intermolecular forces lead to surface tension, lead to viscosity. That's what we need to know. Another last ramification is capillary action. And that is going to be a thin tube where you can have molecules kind of just chasing each other up the tube against gravity. So this is a standard thing for water, for example. So if this H2O at the top is kind of attracting the H2O below it, which is attracting the H2O below that, which is attracting the H2O below that, right? These are all attracting each other. And so we're going to see the water will actually move up even though gravity is pulling it down. The attractive force between the water in this thin tube, the thin tube kind of concentrates the IMF. So a capillary is basically a thin tube which will essentially kind of magnify intermolecular forces. So it kind of forces the water to stay in that happy, this lovely kind of shape. So by having it thin, we can't have molecules that are in a different direction. So we can't have something like this. So this is not going to happen in a capillary as much. Yes, there's also some interaction with glass walls. So that would be in a physical capillary. But in something like a plant stem, you have your xylem and phloem, you have this exact same thing happening. So plants are able to drag water up from their roots, up all the way. If you have a big old tree outside or something, that's hundreds of feet in the air. The water can still go against gravity using these capillaries that are made of cells in a tree or a plant. And so we're going to see that this capillary action, while yes, we can do it in a glass tube, can also happen with cells. So the water molecules will kind of happily go against gravity if it's a thin enough tube. So it happens in plants, happens in glass tubes in the lab. This is something that's just a normal characteristic of life. So if you happen to have thin glass tubes at your house, you can do this. You can just kind of, have a bit of water. You can dip your glass tube in. You're going to see the water will move up. Depending on how thin your tube is, if it's a pretty wide tube, it's going to only move up a little bit. If it's a very narrow tube, it's going to go all the way up. And so you're going to see that this is going to help go against gravity. So yes, Kevin has also mentioned that for glass, water is attracted to glass, or if it's in a plant or something, there are things in those cells that the water is attracted to that again help keep it moving up. Oops. Oh my gosh. So we're going to have kind of two interactions there that are going to help go against gravity. So these are just things that happen. We're going to see that things will move up a tube like this very nicely. Cool. Have we had enough vocabulary for the day? I think we have. I think we should go back to thermochemistry, actually. I think we've been away too long from thermochemistry. So maybe let's go ahead and go back there. Yep, back to numbers. Oh dear. Guess what? It's time for our favorite letter in all of chemistry. Delta H. Yay! We love delta H. So we're going to see that for these two processes, from solid to liquid and liquid to gas, we have specific delta H values for these. This one is called delta H fusion. And this one is called delta H vaporization. Delta H would be different for each substance, of course, because they would be different amount of interactions that you're kind of breaking or messing with. So you're going to see that these would be different for different substances. And guess what you also thought? Do I want to talk about that now? I kind of do. Guess what we're going to be able to do now? We're going to see you are absolutely right. So by Hess's law, here, we can do that. That is absolutely right. Which is equal to fusion plus vaporization. Absolutely. So we had already talked about, like, oh gosh, I don't remember. Did we talk about, like melting being endothermic and all that sort of thing, and boiling being endothermic? condensing being exothermic. Maybe we did, maybe we didn't. Let's just do it real quick. Yeah, we don't have any calorimetry here, so I guess this is okay. Terminology time, I guess. Wow, I just got a very loud email or something. Okay. Here, let's just copy this. Oh no, OLID. Oh, whatever, that's good enough. We'll do this later. We have a fancy term for a solid going to a liquid that's called melting. And of course, melting is an endothermic process. Takes energy to happen. This is called boiling or evaporation. That is also endothermic. And as Shane has pointed out, this process is called sublimation, which, guess what, is also endothermic. Go away. Wow, it tried to tell me solid is liquid. So delta H for all of these would be positive, right? These are all endothermic phase changes. So endothermic, remember, means we're going from like lower energy to higher energy, right? We're absorbing energy. So solid is going to have the lowest energy, then liquid, and then gas. We have the exothermic ones as well. Let's see. Let's paste it. Yeah. Here are the exothermic ones. Good enough. So all these are exothermic, meaning delta H will be negative. The words for these are condensation, freezing, and deposition. So I guess we're still doing vocabulary, but with a few delta H's thrown in. During a phase change, phase means state of matter. Something like melting, yeah, there's your new word. So deposition is the opposite of sublimation. So if you wanted to make dry ice, for example, say you were distributing the potential Pfizer COVID vaccine, you would take gaseous dry ice, and you would kind of really compress, not gaseous dry ice, carbon dioxide, and you would really compress it down, and it would deposit into dry ice, which is solid carbon dioxide, which if you hadn't heard is what the temperature that's needed for transporting and storing the vaccine. So temperature does not change. So while you are undergoing a phase change, your temperature does not change. That is a very important thing here. So this means, for example, ice water is always 0 degrees, and boiling water is always 100 degrees. You know, of course, these would change with pressure and stuff, but we'll just say it. If you have 1 drop of water and all that ice, the temperature of that mixture would be 0 degrees. If you have one ice cube in this whole thing of water and it's otherwise homogeneous, that temperature is going to be 0 degrees. We're going to see here that this is a nice kind of illustration of this point. If you go and start boiling some water, take the temperature of the boiling water when it starts boiling. You'll see it's about 100 degrees. Come back 3 hours later while it's still boiling because it takes forever. Yeah. Of course, it all depends on pressure and all sorts of different other physical properties. But the point is the temperature is not going to change. So if your water is boiling at 96 Celsius because you're at altitude, it's still going to be 96 degrees if you come back 3 hours later. So we know water takes forever to boil, right? To completely get rid of it. So we're going to see here that the temperature is not changing. So graphically, if we were to graph temperature versus the energy that we're adding to the system, we're going to see that we're going to get something like this. As we go. So these areas, that indicates a phase change. So this one would be, for example, boiling. That's where the slope is 0, horizontal line, no temperature change. That's where we're going to have our boiling taking place. Here is our melting. So if we keep adding our energy to this system, and we start with ice, let's say this is maybe negative 20 degrees Celsius, this melting one would be about 0, again depending on a few things. And here we would have 100 degrees, which is where your boiling is taking place. You can use Celsius for this, no problem. Nothing's crazy here. And so we can find the energy added for these steps where m is 0 by just multiplying our moles times our delta H. Nothing crazy. Moles times kilojoules over moles will give you kilojoules, right? Very exciting. If m is not 0, over here it's entirely solid, here it's entirely liquid, and here gas, we're going to see that we have another formula with you are familiar. Oh-ho! You thought we were done with this one. So you're going to use, of course, your specific heat capacity. How exciting. So if we were to figure out this whole thing, if we were to see all the energy required to do this, we would see that we would have a Q for the solid part, a Q for the melting, a Q for the liquid part, a Q for the boiling, and a Q for the gas part. How very exciting. Look, you can calculate it 5 times and add them together just for one problem. Isn't that fun? Thankfully, the math is easy. So we're really only using 2 formulas. We're going to use the MCAT formula 3 times. We're going to have different specific heats and different temperature changes, but our moles or mass would be the same. And for our melting and boiling, we're going to have different delta H's, right? We'll have a delta H fusion and a delta H vaporization. That's a constant. So it's different for the state of matter and the substance. So I can show you a table of, let's see. I don't know, here's some random Google thing. Let's just go ahead and take a look. So, oh, this is silly. Let's see, aha! So here's some specific heat capacities for various things. So, so this is water liquid, this would be water solid, this would be water gas. Notice they all have different heat capacities. We have some other things here. You know, you would have all sorts of various specific heat capacities that would vary depending on your substances. So, yeah, exciting. Lovely. Here's some more, you know, you have all sorts of various things at various phases. So, yeah, exciting. So they're just constants. Though I guess they're not really constants. I shouldn't tell you that, because once you get to real chemistry, not that this isn't real chemistry, you're going to see that it depends on temperature as well. And so your specific heat capacity changes while you are heating it up. But that's not something we'll have to deal with. For us, they're constants. So there we go. Alrighty. We are done for today. Tomorrow is a holiday, no stream. So, it looks like most of you did really well on your exam. If there's anything you want to go over on Thursday, we can do that. Post your screenshots. Yeah. Otherwise, I'll see you next week on Monday. And it looks like I think we've got like about 2 more weeks of lecture, and then we'll figure out our exam, final exam. So yeah, you'll have homework. Don't worry. And I'll also be giving you your lab project topics, hopefully today. So you'll be able to work on those. So make sure that, you know, if your teammates have tried to contact you, that you respond, let them know you're alive. Yeah, so, yeah, don't worry about homework, huh? Yeah, you wish. Alrighty. See you guys next time.